All right, so we might remember that for an sp3 hybridized carbon, the ideal bond angle is going to be 109.5 degrees. If cycloalkanes, again, the cyclic structure of an alkane, were flat, each carbon in the ring would experience considerable angle strain. Also, if a ring was flat, then all the carbon-carbon bonds would be what we call eclipsing. All the carbon-hydrogen bonds would be eclipsing each other, and that would cause considerable torsional strain. In reality, six-membered rings are exceptionally stable and very commonly found in nature. 5-carbon rings and even 3-carbon rings are more commonly found than other rings, but they are not as common as the 6-membered ring. And we're going to spend a lot of time talking about that 6-membered ring in the next set of slides. Okay, we'll start with the 3-membered ring, cyclopropane. Cyclopropane is about 27 kilojoules per mole less stable than cyclohexane per actual CH2 group. And there's a couple reasons for that. First of all, the angles are really tight. They're about 88 degrees, and that is not anywhere near 109.5 degrees, which is where we want to have our sp3 hybridized carbon bonds. We also get torsional strain resulting because the carbon-hydrogen bonds are eclipsing each other or nearly eclipsing each other, as you can see in the molecules drawn below. Now, cyclopropane takes on this kind of puckered conformation that allows it to alleviate some of that strain, but it's still a very strained and reactive molecule. On the other hand, cyclopentane is only 5 kilojoules per mole less stable than cyclohexane per CH2 group. There's very little angle strain. The angles here are very close to 109.5 degrees. There is a little bit of torsional strain. Again, the carbon-hydrogen bonds kind of overlapping each other on adjacent carbons. The cyclopentane can adopt an envelope conformation to avoid most of that and allowing it to exist quite frequently in nature.